Now we start another topic of coloring. So again, we encounter many problems, and then we want to use graphs to extract the essential information regarding the problems. From the problem. And in many cases, we have this kind of a situation where there are some conflicts, and then we want to avoid those conflicts. For example, there are several people, and then some of the people have conflicts so that they don't get along with. And we represent each people as vertices, and then each conflict as edges. And then we want to, say, assign each people to the group, so that each group, there are no two people with conflicts, so that everyone in the group gets along with. Then, we want to assign the group to each vertex, so that the group for this one and group for this one are different. There are other situations that we also have to consider the same problem. There are many situations that you can think of. For example, its vertex is a station, and they communicate using a certain frequency channel. And then if some stations are close and then they use the same frequency channel, then that may cause some jamming problem or noises. So you want to assign different frequency channel to the station, and so on. There are many situations. So it's useful to define some terminology and concept which deals with this recurring problem. So we say that K-coloring of graph G is nothing but the vertex labeling. So in each vertex, we give a value, say F. So in each vertex, we give certain value for a certain set S. And it's called K-coloring if the number of, labels that we use have size K. And usually, we let this S be the numbers between 1 and K. But sometimes, we use different labeling. And the set S is called the set of colors, because we call this color. So assigning certain values here, we consider it as giving a color, red color, blue color, or color 1, color 2, color 3. Each element in S is called color. And we say that it's K-coloring. As we call it the proper coloring. If whenever X and Y are adjacent, they get different color. Then we say this is the proper coloring. And our graph G is K-colorable if it has the proper K-coloring. And we define the chromatic number. And then write this as a KAIST of G. This is the minimum K such that G is K-colorable. And if chi of G is exactly K, then we say that G is K-chromatic number, K-chromatic graph. So we define this concept, and then we define this parameter, chi of G. Now we want to learn about this parameter. How can we find its value? And if finding the value is too difficult, how can we bound it? Can you find the lower bound? Can you find the upper bound? Let's consider some basic properties of it. So there is some natural problem, some natural like non-decreasing property, meaning that if G prime is subgraph of G, then chromatic number of G prime is most chromatic number of G. This is quite natural. If we add on it, that means there are additional conflicts. So coloring, avoiding those conflicts gets only more difficult if you add conflicts, if you add edges. If you delete edges, then there are less conflicts. So this is less restricted. So it gets easier to find the coloring, proper coloring. So this is pretty natural. And another pretty natural example is that if you consider the complete graph and its chromatic number is n, because if you have Kn there are n vertices and everything is connected, then what do we get? Every vertex needs to get a different color. If we give the two vertices same color, then they are adjacent. So it's not proper coloring. So you need n different color, and then n different color is sufficient. Because if you just have n vertices, so you have this. And between these two, what do we know? We know that the click number, the size of largest click, is at most the chromatic number of G. So if you have a graph, and then if there is some click inside here, then all these vertices have to have a different color. And that holds even in this larger graph. Because this click number means that if this is K, that means that there is a click of K vertices, click of order K in G, and then that's a subgraph of G. Okay, so this is one basic inequality. And another property, another basic bound on this chromatic number comes from thinking on what is this proper coloring. So what is proper coloring? If you have a graph, then you color them using, say, red, blue, and say green. No, this is not green. Then the restriction is that the two adjacent vertices get different color. Okay, but in this case, if you collect all the vertices with the same color, then what happens? So you have red vertices here, green vertices here, blue vertices here, then these are independent sets. Because in proper coloring, there are no edges between two vertices with the same color. So, okay, coloring is same as a partition of the vertex set into independent set, K independent set. Then, what do we know? This independent set all have size and most the independence number of G. As the independence number of G is the size of the largest independent set in the graph. Then what do we know? And this shows that the number of vertices in G, which is n, let's say we write it this way, the order of G is at most sum of the size of this K dependent set. Okay, it is this independent set is called the color class of this coloring, and some of the sizes of color class in optimal coloring. And then that's at most K times independent set of G, independent number of G. And here K is the chromatic number. Then what do we get? The chromatic number of G is at most N over alpha G. So you get this lower bound. Okay, so we have seen some basic lower bound on the chromatic number. Then what about upper bound? So in order to find an upper bound, what do we have to do? When a graph is given, we want to show that its chromatic number is at most, say, 5. Then your job is you have to use the 5 colors, or at most 5 colors, to color the vertices so that it becomes a proper color. So you actually have to find the proper coloring using that many colors. And how do we do that? One of the most natural thing to do, if you have a certain graph, then what's your strategy? You give this vertex color 1, and then these vertices now you cannot color it with 1. And let's say 2 and 3. And then here, again, 2 and 3, you cannot color it with 2 and 3. Maybe to be efficient, you use 1 again instead of using new color. And then here 2 and say 1 again. So that's what you would normally do if someone asks you to find the proper coloring. And what did we do here? We take one vertex and then try to decide what color we use. And then you see next vertex and then next vertex. You decide one by one. That's very natural. And if we come up with this kind of certain way to color it, then that provides proper coloring. And then you can analyze it to find an upper bound on the chromatic number. So let's give a name on what we did. So this is some sort of algorithm, whose name is greedy coloring. So greedy coloring with respect to a vertex ordering. So let's say vertex ordering is B1 to Bn. This is ordered, or the vertices in the graph order. And then what it does, it colors the vertices in the order B1 to Bn. And what we do, we're giving its Pi the least index color, not already used on its neighbor. So you assume that the colors are also ordered, and then you take one by one, and then at the moment you see this vertex, and then see what colors are available, and then you choose one of them, and then you color. So just like what we did here. Then this is an algorithm, and we know that it will give us proper coloring. We don't know how many colors it will use, but it's surely that it gives us proper coloring. And we can analyze how many colors it will use at the worst case. Then we get the following proposition that the chromatic number is at most the maximum degree of G plus 1. Now proof is pretty straightforward from this algorithm. If you consider any vertex ordering, So recall that this coloring, this algorithm, depending on the vertex ordering, if you take a different vertex ordering, it might give you a different proper coloring. But in any vertex ordering, we know that each vertex has at most, let's say each vertex P has at most how many earlier neighbor? Degree, each degree, which is at most delta of G, earlier neighbors, which is already colored at the moment you consider this P. So what? The greedy coloring will not use more than delta of G plus 1 color, because it has at most delta earlier neighbor, and out of delta plus 1 color, at least 1 color is available for that bird. So you can choose one of the, one of the least indexed one, and you keep go. Okay, so we obtain this upper bound. And then once we have this kind of a bound, what do? We try to see how good bound it is. Is it best possible, or can you improve it? And you can easily see that if you take a complete graph, Kn is maximum degree is n-1, its chromatic number is n, which is delta plus 1. So this is best possible. This is tight. This inequality is tight or sharp. If we say that this is tight or this is sharp, if there are examples with the equality, so you cannot improve it further. If you subtracted one, then it's no longer true. And also there are other examples, say the maximum degree of a cycle of odd length is 2, and its chromatic number is 3. It's easy to check. So this is tight. Okay. However, later we will see that this is rarely tight. This is tight, but it's very rare case that it is tight. Later we will see that these are pretty much the only connected example with the equality. And then for the rest of the graph, we can actually improve it. But we will prove it a bit later. And okay, even if this is tight, maybe we can get a better upper bound for, if we know certain more information about this G. So one of them was this, as I mentioned. As long as it's not one of these two, then we may improve it, but we will do it later. And one thing that caught our eye is that we didn't really care about the vertex ordering in this proof. There are n factorial ways to order the vertices. Then it feels like there must be some difference between those orderings. For some orderings, it might be better. For some ordering, it might be not good. Then we can try to come up with the best ordering. And then maybe this greedy coloring algorithm give you a better bound. Okay. But if you see this proof, then what's the important thing? Important thing was this number of earlier neighbors. Wait, why did it go away? Okay, here. Then how do we minimize this number of earlier neighbors. For example, if you have a vertex and then like any leaf attached to it, so this is a star. If we order it by 1, 2, 3, 4, 5, then what happens? At the time of considering 5, there are like 4 previous neighbors. It has 4 earlier neighbors. However, if you consider it different way, this is first, 2, second, third, fourth, fifth. And this has 0 earlier neighbor, and then all of this has only 1 earlier neighbor. So this is better ordering in terms of number of earlier neighbors. And if you see, putting this vertex with high degree at the earlier stage so that it doesn't have an earlier neighbor is the strategy for minimizing this earlier neighbor. In other words, we want to take the vertices with a small degree, we want to put it at the last. Then, since these are the last one, that means this happens before, and then this vertices with high degree sends lots of edges to the later neighbor. Then it has smaller number of earlier neighbors. So this gives you this motivation for the following definition. So in this ordering, what was important is that the V1, V2, V3, Vn. And at the time of considering Vi, we take a subgraph G of V1 to Vn and Vi. And there, what's the degree of Vi? That was the important thing, right? The degree of G V1 to Vi of Vi. That's the number of earlier neighbors here. And we want to minimize it. And that gives you the motivation for following definition. A graph G is K degenerate if every subgraph has a vertex of degree and most K. And so we want to make sure that, so here, what are the strategy? We put the vertices with the low degree at the last. So we want to put this as a smallest degree. And at the time of here, we want this to have the smallest degree in this graph. So this degree is actually minimum degree of this subgraph. So we are caring about this minimum degree in subgraph. And we define the degeneracy. Of G is that you take the subgraph out of subgraph, you take the minimum degree of this H, where H is the subgraph of G, and then you write it for all H, and you take the maximum out of it. So that is the minimum K such that G is K degenerate. And we give name to this concept, which motivates to define this degeneracy. It is the smallest last ordering of one n vertex graph G is constructed iteratively from the index n to 1. So it's backward by setting vi the vertex of minimum degree in the graph G minus the larger index, which is same as the graph. Okay, at this moment, V1 to Vi is not defined, so this is better. So for, say, this graph, you put this as V6, and once you delete it, this is degree 1 smallest, so this is V5, and then this is degree 2 in the remaining subgraph, so this is V4, and then this is arbitrary. So that's the smallest class ordering. And here again, this is V5, this is V4, V3, V2, V1. Okay. So this is what we define as a degeneracy. For example, there are certain graphs we know the degeneracy. If you have a K-regular graph, it has degeneracy K. Why? I mean, the graph itself is a subgraph of it, and its minimum degree is K. So its degeneracy is at least K. And every vertex has degree at most K, so the degeneracy is at most K. So this degeneracy is exactly K. And also, another example is any tree has degeneracy 1. Non-trivial tree. Meaning that, one vertex graph is also a tree, but it's not, its degeneracy is 0. But the other tree have degeneracy 1. Why? As we learned, a tree, every subgraph of it is a forest. And in forest, we know that either it has an isolated vertex or it has at least one leaf. So a vertex of degree at most 1. So in any subgraph of tree, the minimum degree is either 1 or 0. So it has degeneracy at most 1. And it has degeneracy at least 1. It's also easy to check. The tree itself has a minimum degree 1. Okay. Then what do we have? Using this concept, if you apply this proof again, then it's easy to check that the following properties hold. If G is K degenerate, then this K plus 1 parallel. And then proof is identical to the previous, proposition. So for example, it's 3. If you apply the maximum degree plus 1, then that's what? 5. But this is 1 degenerate. So this is 2 parallel. But this here is a better bound. And sometimes the degeneracy plus 1 is called the Chromatic number. But this is different from chromatic number. And there are natural examples. For example, if you consider K and N, it has degeneracy, N. But the chromatic number is only 2. So we have this bound, but still, I mean, it's not really pinpointing the chromatic number of graph. In fact, the pinpointing chromatic number of a graph is a difficult problem. It's a NP-complete problem in general. So we don't expect to actually find a very concise and concise formula which computes the chromatic number. What we can do is finding some general bound and then find some better bound for graph satisfying certain good property. Or we find some relationship between this chromatic number and other graph parameter or other concept of the graph. That's what we will do. In the next several video, we will discuss the relationship between this chromatic number and other concepts, and then we will prove further theorems on this. Okay, then I will see you in the next video.